So the last section is about multiplying vectors together. And it's a little more complicated than it may seem because there are actually two types of multiplication. There's one called the dot product and one that is called the cross product. And they are used, the dot product is used first when we calculate work. The cross product is used when we talk about torque and also when we have things involving magnetic field. So we're going to introduce the kind of the idea behind what they mean for right now, more graphically than what they mean when we actually use them. So, and we're going to do this all using components, using the IJ variety. So what we're going to have is we're going to start with a vector A, and it's going to have an X component that's in the I positive X direction. It's going to have a Y component that is in the positive J direction, and a Z component in the positive Z direction. So these are the unit vectors in the different directions. Then you have vector B, which has your X component, your Y component, and your Z component. So we can generalize. We're actually going to, let's actually just let me erase this right now, because graphically what they mean is a little bit easier to do in 2 dimensions. So let's say we have 2 vectors. Let's just draw them. So let's say vector A is here, and vector B is right there in that direction. Okay. So this is vector A, and this is vector B. And there's an angle theta between the 2 vectors. So this theta is not relative to the coordinate axis. It's the angle between the 2 vectors. Actually, they use phi because we've used theta before. So let's use phi. Phi is a Greek symbol spelled like this. Phi, phi, pho, pho. So the dot product of the 2 vectors we would show as such. We would say vector A dot vector B. Now, in terms of numbers, if we had 3 times 4, we'd say that's 12. It's just simple. So sometimes we use the dot to represent multiplication. Now, in vectors, it means a specific kind of multiplication. And what it is graphically what it is when you do it in this direction, it is the A dot B is going to be the component, actually it's going to be the component of the B vector in the direction of vector A. So what that represents is the component. There's 2 components. There's the X component along of vector B along vector A. So those are 2 parallel to each other. And then you have the other component that's perpendicular. So remember, components are always perpendicular to each other. So this is a 90 degree. Notice this isn't horizontal. This is at an angle. But they're relative. The X component of vector B in the direction, or the component of vector B in the direction of vector A, that is what this thing represents, this vector there. So that's one case. Let's look at another case just to show you how it works out. Let's say your 2 vectors look like this. Let's say vector A goes this way, and vector B goes. Actually, I'll change the color here, so we're the same color. So vector A is like this, and vector B is, in this case, I'm going to make vector B longer than vector A. Okay, so that's vector A, that's vector B. The angle between the 2 is still phi. what we do is we're going to take vector A, and I'm just going to extend it. So this dotted dashed line has the same direction as vector A. It's just longer. It has a longer magnitude, and you'll see why I did this in a second. So this is vector A. This is vector B. This is vector A just made longer, arbitrarily longer. So if I wanted to show the two components of vector B, where one component is in the direction of vector A and one is perpendicular to the direction of vector A, I got to make sure those are mutually perpendicular, so I'm going to make that a little shorter. So this blue vector here, I'm going to sneeze here. Excuse me. So this blue vector is going to be A dot B vector again. So that's what happens when one's shorter than the other in that direction. If you now, let's say you have vector A goes this way again. So this is vector A. Vector B goes this direction. So what is A dot B? What you do there, you extend vector A, but in the opposite direction. So it goes like that. So again, it's in the same direction, and it can extend both this way or that way. In this case, I just extended it that way because that was the one that made me get a right triangle. So I can then take vector B here again, and I can break it up into two components. One that's parallel to vector A and one that's perpendicular to vector A. And so this vector now, which is going the opposite direction, this vector here from here to here is going to be A dot B. So again, this was vector A, which was going from here to here. This was vector B. This vector, the blue vector, is vector A, vector A dotted with vector B. And actually, one thing I didn't point out correctly is the dot product is this distance. It's not a vector. So this vector A dotted with vector B is a distance. It's a scalar. So let's go back to the original one. So A dot B is not a vector here from here to here. It's just the length from here to here. Let's write that down. A vector dotted with the B vector is a scalar which has a value equal to the length of, now it can be negative, so it can be positive or negative, but it doesn't have a direction. So equal to the length of the component of vector B in the direction of vector A. So that's the gist of the what the dot product is, and it's important in calculating work. Is one of them. What we want to do is, in that case, we have force. Force is one of the vectors, and displacement is the second vector, and you want the component of the force in the direction of the displacement. We'll see that more later. But from a mechanics standpoint, just that's graphically what it is. For the most part, if you keep things straight, you don't really have to worry too much about it. But let's go back to the general case of a three-dimensional vector. So we've got this again. So we got three components: the x, y, z direction. You've got vector b. So the actual, if I say what is the value of a dot b, what you do is you take the x components and you multiply them together, and you add that to the y components, multiply together. Or is it multiplied or is it added? I think it's multiplied. Yep, they're multiplied together. And notice there's no direction associated with this, so I'm using the components. So you take this times this plus this times this plus that times that, and you get a number. And that's the dot product. So that's pretty easy to do. Now, going back to the original drawing, you can also, from geometry, you can say that the value of vector A dotted with vector B turns out to be the length, the magnitude of vector A, which is a number, scalar, times the magnitude of vector B times the cosine of the angle phi between the two. And that comes about because, how does that come about? Yeah, I'm trying to remember how that comes about. It ends up because of this right triangle that you end up with here. And I'm trying to see if they explain how it works. I think it's from the law of, no, it's not from the law of cosines. Or maybe it is. Anyway, I can't remember exactly if they tell you what it is. And so in this case, phi is between 0 and 90 degrees. So this is going to be a positive number. And so when you multiply this times that, the magnitudes times cosine, that's going to give you a positive number. Now if you come over here, this case, the angle phi is this right there. So in our first two cases, phi was going to be between 0 and 90 degrees. In this case, when they're going opposite directions, phi is between 90 and 100 degrees. And the cosine of phi, in this case, is less than 0. So you get a negative sign from the cosine of phi, and therefore that's why you get a negative number when you do the dot product of things that are not going in the same direction. And you always measure you could measure the angle all the way around here, but you always measure the angle so that it's either between 0 and 90 or 90 and 180. So again, here, this is the angle, the smallest angle between these two vectors. This angle here is also valid, going from all the way around here. It's valid as far as geometry is concerned, but we wouldn't use, if this was 30, I wouldn't use 330, even though that is an angle between those two vectors. Likewise over here, if this angle is 130 degrees, I could also say the angle between the red and the black vectors is 230, 360 minus 30. But we always use a value that's going to be between 0 and 180 degrees, and that makes sure the sign of the dot product is appropriate. So one thing about dot products is if you know the two vectors and you know the length of the two vectors, you can actually use this relationship here to solve for the angle between the two vectors. Now we don't normally we give you the angle in physics, but if you do vector calculus, you can solve, you can say the cosine of phi is equal to the dot product, which we know how to do, divided by the magnitude of the vectors, which you can find those by using the Pythagorean theorem, and that gives you the cosine of the angle. So given two vectors, you can always know what the angle between the two vectors is by using this relationship. Let's just demonstrate that because it's kind of cool. So what I'm going to do is I'm going to actually put a graph paper up there. And this works in 3 dimensions as well as 2 dimensions, which is super cool. It makes the whole, if you take statics, if you take engineering statics, you use these relationships a lot. So I'm going to pick 2 vectors. This is going to go right out to here. So that's one vector. And then I have a second vector going to there. So the angle here looks like it's about 45 degrees, but we don't know for sure. Vector A, which is the red vector, is 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 units in the I direction plus 1, 2 units in the J direction. So that's vector A. Vector B is 1, 2, 3, 4, 5 units in the I direction plus 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8 units in the Y direction. So what we can say is, what is the angle between those 2 vectors? This angle right here. Now one way you could do is you could calculate the angle between here and here, from the x-axis to here, and you could calculate the angle between the x-axis and there, and then you could subtract the 2 angles. And that would give you the answer. This is a quicker way of doing it. So the cosine of phi is going to be equal to vector A dotted with vector B divided by the magnitude of vector A and the magnitude of vector B. So let's do those 3 things. So vector A dotted with vector B, put this here, so it's vector A is 8I plus 2J dotted with 5I plus 8J. And dot product is you multiply it, so it's just you multiply the x components together and you multiply the y components together. And so that's going to give you 8 times 5 plus 2 times 8, which is 40 plus 16, which is 56. So the numerator is 56. The magnitude of vector A, using the Pythagorean theorem, is going to be 8 square root of 8 squared plus 2 squared, which is going to be the square root of 68. And that's 8.246. And the magnitude of vector B is equal to the square root of 5 squared plus 8 squared. 5 squared plus 8 squared, square root, which is 25 plus 64, which is 89. So it's the square root of 89, which is 9.344. 9.434. So I can put those up here. 8.246 times 9.434. So you get 56 divided by 8.246 divided by 9.434. And I get 0.7199. So the cosine of the angle phi is 0.7199. So phi is equal to the inverse cosine of 0.7199. So I take the inverse cosine of the answer, and I get 43.9 0.96 degrees. And if I go back and I look at this, you can see it looks like about 49 points, not as in like 43.9. So it just looks like close to 45 degrees. That was my estimate. So that's pretty interesting. So because it took a lot of time, I'm going to do a separate one on the cross product. But so in review, just quickly review, the dot product between two vectors is the component of the second vector in the direction of the first vector. The components are going to be parallel and perpendicular to the first vector. So this is the component of B in the direction of A. This is the component of B in the direction of perpendicular to the direction of A. The dot product is the length of this vector, the length of the vector in the direction. Come on, good. To actually do the dot product, you multiply the components of the vectors together and add those products together. You get a number. It's a scalar, not a vector. You can also use, there's also this relationship that relates the dot product and the magnitudes to the angle between the two vectors. And so any two vectors in 2- or 3-dimensional space, you can find the angle between those two vectors by solving for the cosine of phi, doing the dot product, getting a scalar, doing the magnitudes, which are scalars. Everything is scalar, so you get the cosine of phi, which is a scalar. You take the inverse cosine of that, and you get the angle. Super cool.